first thing, my name is Greg Belladue. This is mostly, no, this isn't mostly new people. You're the same people that have been in except you two. So it's fine. I guess you haven't been in my life either. But that's okay. So my name is Greg Belladue. I am a solutions architect for a company called Ionic. That's a fancy word for I'm a programmer. And this is other Greg over there.
Can I get everybody to look this way? I'm the official obnoxious photographer.
He's the official Greg. I'm just Greg.
Thank you.
No worries. I help my company makes a framework for developing phone applications. Good. And so as a solutions architect, I teach corporations how to use the tool. So basically I mentor corporations. Day to day, I stare at a lot of code that I have not written and try to comprehend, understand it, and help them get directions to fix the issues they're seeing. So it applies a lot to robots because then I stare at kids' codes that I have not written and try to understand and comprehend. And so this is my 18th season of FRC. I've been doing it a long time. On the team, I'm not a programmer. I help out, but that's not my main focus. I let the smart people do that, and I just come in and make demands and then run away, and they love me for it. So today, I'm going to be talking about simulating. I don't think, so if you're planning to follow along, I apologize, I'll probably be moving a little fast for that, but this is all being recorded. We'll post this up, and I will probably actually get this repository up on GitHub so you guys can look at it with the presentation. But just focus on following along, and maybe not, don't worry about trying to code along with it, okay? So I'm going to be explaining a couple things today to start off with before I sit down and start coding. With simulation, you are essentially trying to mimic the hardware on your robot in software. And that's hard, right? You have, because of what we would do with physical products, like, okay, if I'm simulating like my phone app, that's really easy to do. But simulating something that exists in the real world with gravity, with friction, with odd lighting is hard. And so a lot of the focus today is going to be on how to, one, structure your code such that you can separate the simulation code from the real robot code, and two, just how to set up a whole project to do some simulation. I'm going to be trying to write as much simulation code for our 2023 robot with you guys as I can. Ideally, that means simulating the arm and the elevator together. So to jump right in here, we're going to talk about architecture first. With simulation, like I said, you have to think about your simulator as separate from the real robot, because you're not going to be simulating your Spark Maxes. You're not going to be simulating the Falcons. You need to think of your robot almost as what's called like a black box, that it does these things. It can drive this way, it can swerve, the arm can go up and down, but we don't care in simulation what motor does that, okay? We care what signals you send the motor, okay? So you're gonna be sending, like with motors, you send voltages. You send between negative 12 volts and 12 volts to do the things you wanna do. You throw those into a PID controller to make it smooth and go up and down nicely. We do care about that and keep that integrity. But we don't care that you're sending those to a Spark Max. We're not going to do any of that. We are going to be using, WPILib has a series of objects that help provide the physics simulations that you need to feed your logic into it. So the hardest part about all of this is understanding how to lay out your code to do that, because it's very easy to just try to throw all of that code into your the same like class file as the rest of your logic, right? There is helper functions there where I think there's robot.isReal that you can use that'll return true or false if it's a simulation or not. And what I'll see frequently is kids that just do an if statement. Is robot real? Yes, okay, do my other stuff. Is it not? Okay, do my simulator stuff. And it becomes this big like hot mess of if of all this logic. Which from like a perspective of good code, what I tell my customers, that is not maintainable code. All right, there is basically two systems of logic flow going on, but they're like intermixed like a sandwich, right? And that's not great. So what we started doing is we took from team 6328, I believe, Mechanical Advantage. They make Advantage Kit and Advantage Scope. They do a lot of cool software things, and if you're not using Advantage Kit and Advantage Scope, I highly advise that you do. But they lay out their code in the following way. So is everyone here, if you're not new, which I think you guys are new, no, it was the other members of your team that were new, familiar with the command-based robot project? Yes? Yes? Great, awesome. So we're going to use command-based, and command has two big things. It has subsystems and it has commands, right? Subsystems are where all your logic goes, and commands are where all your like base logic goes. So when you say you want to move 10 inches, it sends the signals to your SparkMaxes, and maybe it does it nice and smooth with the PID controller. But commands are you string those together to make it do really cool things, like move forward 5 inches, then turn right, then move forward, then move your elevator up, then your arm, and all this cool stuff. Those are your commands. For simulating, we are going to take the subsystem and break it down one more layer, okay? So I've drawn it up here. So this big overarching box, that's your robot, okay? You've got then these three here, which just happen to be random subsystems. So you might have like your drivetrain subsystem, you might have your arm subsystem, and you might have your elevator subsystem, okay? These big three things. Then inside of there, you have your commands, okay? So I just drew one command. And then you have your logic, your business logic, okay? And that's what usually your subsystem is actually filled up. Because a lot of the times you actually take your commands and put them into a different file. We're not going to do that today just to keep things a little bit simple. But you have those commands, and then you have like the logic that those commands drive. Again, I'm using a PID controller as an example here. A lot of the times your subsystem just maintains a PID controller and a bunch of like SparkMax objects, okay? We're going to take that logic and break it one more layer. We're going to add what I'm calling an I/O layer, or a hardware layer. And that is right here. And so that layer is only for talking to hardware. So in this case, what we're going to do today, all it's doing is saying, give me my current position, and here is a voltage I want you to apply to whatever you're doing. Two methods: get position, apply voltage. You then, this is where you break your simulator from your real robot. You write that I/O as like an interface. Today I'm not going to be diving into like how to write Java. Like I'm not going to be talking about what an interface is. I may talk about, so I'm going to be using one of the Java 17 features. I'll talk about that real briefly. But if you've got language questions, we'll save them for now, okay? So you're going to have that I/O interface with those two methods: get values, send values. You're going to implement that interface twice. You're going to do it for your real robot, where then getting values has like a CAN SparkMax, where you get values from it. Maybe you read from an encoder that you've got, and you read from that and you send it back. And then the send values is you're sending a voltage to that CAN SparkMax, which translates to your actual robot. You've got the real one there. Then you have your simulator, your sim robot. And this one doesn't have a CAN SparkMax in it. This one uses a helper object from WPILib that has the exact same utility as a CAN SparkMax, and actually starts to add gravity and inertia into the situation. But you're then just asking it, what's my current position, and setting it voltage, and it will perform a physics simulation per loop. I apologize, I'm getting over COVID. I tested negative today, which is great. But it'll apply that per loop to do your physics simulation. That is the bulk of the difference between a real robot and a simulated robot. We'll be adding another class in here to visualize that in the system, so you can actually do all this at home and test your robot at home and verify things. I do want to make one thing clear here. So with FRC programming, there's kind of two big different programming tasks in the context of what I'm talking about. There is your architecture and your flow, making sure that like when the driver hits the A button, that it tries to move the arm to 45 degrees or tries to bring your elevator up and down. And then that's one big aspect of programming. That's actually a lot of like the bulk of the actual code that you guys write, is you're just writing architecture code. That obviously doesn't make the robot work. There's the other half where you're just writing tuning. You're tuning your controllers, you're tuning your max speeds, etc., which is very minimal code, but is a lot of time and effort spent with that. Simulation, you are not doing any of the tuning. Tuning should only be done on real hardware, okay? You can do tuning in here, it's gonna be wrong, and I'll show you that. And we'll do a little bit here just to make the simulation work, but it's going to not translate 100% to your real robot. What you're gonna be doing for simulation is the big picture items, making sure that the arm is going to go the correct direction, making sure that it's doing things in the right order, okay? It's saying, okay, elevator goes up, then arm goes down. But you're not actually tuning, that kind of stuff. You use the real robot for that. Yes, sir.
So the tuning is sort of, as I understand it, the tuning is sort of the bridge between the simulation and the real world. The simulation is idealized, whereas the real world is not.
Yes.
So the tuning kind of adjusts
Yes.
what you would be doing in simulation for the real world.
Yep, simulation, you're doing fake physics, and boy, you could probably spend a lot of time and get it really, really close to reality, so that you could do tuning in sim. But no, tuning, you're overcoming friction, you're overcoming your gearbox, all that kind of stuff. So today, one big thing I want you to take away is you're not using this for tuning. You're not going home and trying to make your autonomous mode run a quarter second faster. You're using this to lay out all the steps of your autonomous mode, roughly, that you can then take back once you have the real robot in hand and start to shorten those and tune those and make those work. So I'm going to be doing some code here. If you guys have questions, either yell them out or maybe one of you guys can watch for hands that go up, because I will not be looking too closely up there. So today I've got over here basically a bare robot project. Is this font big enough for you guys? Okay, Steve, yeah. Basically all I've done is created a new project and I added Advantage Kit to it. I didn't want to do that here because I don't know if the internet's great or anything and that requires downloading. But otherwise, this is a bare command project with a lot of the comments deleted out and all the extra stuff we don't need deleted out. So we're going to start by doing the arm. So what I'm going to do first, make a new folder. I'm going to call it subsystems. We're going to make a new folder in there for the arm. And we've got that. So I'm going to start with, we're going to start with one more. We're going to do the I/O layer first. So I'm going to make another folder called I/O. In this, we are going to, what do I want to call this one? I probably want to call this one ARM.io. Yep, ARM.io.chop. In here, it's going to be an interface. And now I'm going to define public object. And I'm using object for now. It's wrong, but doing that to scaffold this out. Get state and public void set state. And it's going to take some objects. Who knows? Okay. This is what I talked about before. I/O stands for inputs and outputs, and we are going to define two methods. One that gets the inputs, one that sets the outputs. We need to define what those look like. You could just do this as like a double here, and instead of get state, this could be like get position, and then you could have another one that's like public double get velocity, and that's entirely okay as well. I like to containerize these just a hair so that it's a little bit of a simpler interface and add some structure to it. So we're going to make that class right now. So I'm going to call this armstate.java. This is the only place, .jav, yeah, okay. This is the only place where I'm going to use a new feature here of Java. So, of course, because I didn't do it .jav or .java, it didn't do the auto generation for me, so give me 1 second. There we go, new file, armstate.java. Cool. So we're going to use a feature called records. And so what a record is, this is the only bit of Java language that I'll explain because it's new. It's new in FRC. You can use this next year, Java 17 will be standard for FRC. A record is a class, but it has all its constructor objects, or everything that gets passed in the constructor is what's called immutable. It means it cannot be changed. So I'm going to say right here, and I'll show how this works, input state. It's basically shorthand for a class. It defines the is equal method, it defines the toString, all that for you. And you put it all into the constructor here, which has a little bit different syntax. Current angle degrees, if I could spell, and double current velocity degrees per second. So when you make one of these, what you would do by saying like private input state I equals input state 10 and 10, whatever. If I could spell input state right. You make it the same as anything else, but if I were to try and change that current angle, I dot current angle degrees. Why did it do in? It gets mad because this is immutable, which means it cannot be changed. The reason I use this is because everybody, all your students, all you guys are learning how to program while you do this. And you guys may be the seniors, and you're going to have freshmen on your teams that are writing code. My biggest goal with any code that is written for this robot is to make it as hard as possible for someone who doesn't know what they're doing to break it. Does that make sense? Like, I don't want you guys to write code for a drivetrain, and then when the freshman is going and writing code for an arm, he somehow turns your drivetrain from swerve drive to tank drive in an entirely unrelated context. And writing sloppy code can do that. Making this immutable means it's very hard to change. It means that you need to be actively trying to change it. Okay? So that's all this does. You could, of course, define this as a class if you wanted and do all that. Or you could not do this at all, but I figured we'll talk about one cool Java 17 feature today. Maybe we'll talk about two. So then we're going to have the output state. And this is what you send to the robot, or you send to your I/O. I'm using, so when I said there was only one thing I was going to explain, there's actually two. I'm using this optional character, which basically, the biggest issue with Java is null pointer exceptions, right? When you can't catch those in compile time, when you run the robot, you'll get a null exception because you forgot to define something properly. Optional is another one of those things that makes it a little bit harder to define something as null. So it just makes it harder for someone who doesn't know what they're doing to break your code. It'll pop up a big red compiler error instead of a runtime error. That's the biggest thing here. And then just to keep using this a little bit more than you really need to do, I'm going to do a goal state as well. I think it should be clear here that you don't have to use records. You don't have to do this the way I'm doing it. This is just a little bit superfluous, a little bit extra, but to try and separate your logic into different classes. So we've got this arm state class. This is all we're going to do to it, is we define these three records for us. So we go back to our arm IO, and now we know that we want this to be arm state.input state, and we want this to be arm state.output state. And I'm going to rename this. And so now we have our two methods that we need to define. Give me all your inputs, take all my outputs. So let's do that. Let's make a arm sim io.input Java. And now we should start moving relatively quickly here. There was a lot of setup, but implements ARM.io. So we've got to implement those two methods, the get state and the set state. All right, so here is the first cool WPIlib provided object. It is called single jointed arm sim. They provide you a class specifically meant for simulation. And so that's what we're going to use. It takes a dozen parameters. I highly recommend you guys get used to reading documentation, because documentation is the biggest, is one of the most important skills to have as a programmer, is understanding how to read documentation and being okay reading documentation. So here's what we're going to do. The first parameter is you tell it how many and what kind of motors it's using. You use this DC motor class that's provided, and we are going to use Neos. So it's got to get Neo, and you tell it how many. We're just going to use one. All right. The next, I really don't like this keyboard. The next parameter is the gear ratio on your drivetrain, or on your mechanism. And so this is based on what your CAD team designs. We had a 50-to-1 gear ratio on there, so we put 50. God. So now if you look at these next ones, this next one's a little bit scary looking, right? It says like joule kilograms per meter squared or something. It's basically inertia. Here is where you can do a couple things. There is a helper method in here that lets you do that, and this is where the physics gets wrong. The helper method assumes, like if I had this box, if I hold it close to my body, is really easy to do. If I hold it out here, it's a little bit harder to do, right? It's the same weight, but now suddenly it's 3 feet away from my body. Now it's heavier to do this, whereas before doing that's really easy. That's what this inertia is trying to do. The calculation it's going to do assumes that it's a uniform weight. If your CAD team designs everything in CAD, you can actually grab the inertia out of your CAD program and you could put it in here. This is probably good enough. So you use another class. This is why I didn't want you guys to try and like follow along with your code, and I'd rather you guys just pay attention and then grab it from GitHub, because it's a lot of just what class do we use. Another single jointed arm sim, estimate moment of inertia. You tell it how long it is and how heavy it is. We're going to use a helper class here that you guys should all be familiar with, the units class, to turn inches into meters. We're going to say it was 25 inches. And we are going to use another one, units.pounds to kilograms, and we are going to say it's 20 pounds. Okay? Units are the biggest thing that can get you in trouble. Make sure your units are consistent throughout everything. That's why I defined this guy up here so explicitly. Degrees per second. All right, the next bit here, is there a question? Yes. They used inches when everything else was in centimeters, I believe, and so it just full sped into the moon or something. So I'm just going to fill this other one. That last one was, again, the length of the arm. This next one is the minimum angle that it can be at in radians. And so that one, if you remember your unit circle, I'm just going to say it can do a full rotation backwards. Your max rotation, I'm going to say it can do a full rotation forwards. And like I said, this first bit is a lot of munging. It'll get fun. This last one here says simulate gravity. Always good to probably just say true here. And so now, when I said before that that your sim is not going to do CAN-SPARC maxes or any of that, this is your CAN-SPARC max right here. This part gets really easy. So I'm going to get rid of this auto-generated. I hate the amount of comments it makes. The one like trick here is you need to tell it to move forward 20 milliseconds in its simulation. So you say sim dot update, and the time, we do 20 milliseconds. And then, when we get our state, we just say new input state. And our two parameters were, it was angle in degrees. So the sim has this method called get angle rads. We'll change it in a second. And it has sim.get velocity rads per second. Remember, I defined this as degrees. So we'll use the units again. Units dot degrees to radians. Sorry, we want radians to degrees. This keyboard has the page up and down arrow key or buttons right next to my arrow keys, and I keep hitting them. And then we'll do the same thing here. So this converts it from radians to degrees just so that it's in the same units as ever. Set state, this one is really great. All you say is technically the sim has set input voltage, and you would tell it how many volts. The only complicated bit here is because we defined it as optional, we need to make sure that it's not null, or else it'll throw an error. So we say output dot voltage, that's provided there. This is an optional. We get to use this cool method called if present, which basically it will call a function inside of here if this returns true. And we just say volts. And we're gonna wrap that. Is that one too many? Might be. There we go. There. So, grabs the voltage. If that is not null, it calls this lambda, this function, which is set input voltage volts. And that is our simulation. That is our ARM I/O here. This is the code that you have to write that's different than the rest of your code. All the rest of the code that you're writing for your ARM translates between your real and your simulator. So let's do that. We're going to make a subsystem class. We haven't made that yet. ARM subsystem.java. And I'm going to speed through this one a little bit because this is nothing new. I believe I extend subsystem base. Yep, there we go. No, don't have to implement IO here. This is where we're going to have, we're going to have this ARM subsystem. And here is where you would have that like if robot.is real or not. You define it right here by saying that the constructor takes an ARM IO. And so if this was real, you would pass it the IO that you implement, which I didn't implement here, but I can do it real fast. ARM real IO.java. Oh, not .ja. This keyboard's got some funny lag on it, which just ruins me. Implements ARM IO. And in here, you would probably have like spark max. We'll just do spark equals new spark 1, etc. And you would say something like spark dot set voltage output dot voltage. I'm going to comment this. I'm not going to actually implement this one, but you kind of get the picture here. This is where you would say you'd probably have an encoder, and you would say like get encoder value, return it here, etc. Does that all this makes sense, right? This is where you would usually have a lot of your subsystem code, or a lot of your hardware logic here. So I'm going to, put that return back there. So in here, you would either pass an ARM real or an ARM sim, depending on that if robot that is real. That's kind of the magic hookup right here. Go for it. Yes, exactly. Polymorphism. So I'm gonna save it off right here. Not finale, final. Again, final is one of those ways that makes it really hard for your freshmen to break stuff because it'll throw a big old error. this.io, and I'm going to define a couple logics here for, this is what we did for our robot. So I'm going to do a profiled PID controller. I'm going to use another class that they've got called arm feed forward. And this is the two objects that kind of control all the movement on our arm. Profile PID controller, we're just going to keep that as 0000 for now. New constraints 00. Import that. Make sure we don't import swing. Find my end key. Enter this.ff equals new arm feed forward. Again, all zeros. If you've never looked at the feed forward or PID controller stuff, there's some great WPI lib documentation on it. Just go find it there. But it's basic logic where, like, feed forward, you combine the results of the feed forward and the PID controller to create a voltage that you output, and I'll show you that here. All right, that's all we're going to do in there. We're going to then do periodic. So you guys probably have this in your stuff. Just one check here, because you don't want this to run if the driver station is not enabled. And actually, we're going to add one more thing. We're going to add private arm state dot input state current state to the top. And we're going to save this off. So we're going to say current state equals this.io .get state. So that's the key right there. This is where we're using that IO layer. We're getting all the inputs. We say the effort, so we're going to create the output voltage now. So we say this.controller.calculate, and this is using that PID controller. So we say current state, if I can type, current angle degrees. And one more thing, I created that goal class, if you remember, which was kind of superfluous, but this is like the position you're trying to get to. So you would be manipulating this goal over time. You'd be saying 45, or make it 60, or whatever. We're going to start off with our default goal of being 45 degrees. And then in here, this controller, you pass in where it is now and where you want to be. And so it creates a value for you. Feed forward is similar, except we have to do a bunch of stupid unit conversions because it wants radians. And this one is, so the first one is position that it wants, and the second one is velocity to calculate your feed forward. Okay. And so now the value you feed into your output is just the combination of those two doubles, effort plus feed forward. Then you say this.io .set state, new arm state .output state, and this is where it makes it hard for your freshmen to break things because that's not defined, right? We made this optional, and so you can't just pass a double. You have to say optional dot of, not double, of effort. It's a little more code. But what we are doing here is we are defining the intention of your class. It's a little bit self-documenting here, but it's basically saying that you need to be clear. Is this a value or is this null? Because if it was null, you would say .empty. And it is a little bit more code, but it defines or it describes the intention. We're going to make one more method for now. That is to get the state that we're saving off every loop. Okay. So for now, this guy is basically done. That's all the logic. The only other code we're going to add to here is manipulating this goal and changing it from different positions. And in fact, let's go ahead and do that real fast because it's easy. So these are where we're going to put our commands. We're going to do one command, set arm position, double degrees, where it's going to return a command that changes the arm's position. We're going to use some of the helper stuff that is in WPILib. These are called functional commands. These are where WPILib is going towards. So you may have had commands where you define a whole command object that extends command base or something and has a constructor and all this. They are moving away from that and into these, what they're calling functional commands, which are a lot less boilerplate code to do the same thing. And it's just mad because I need to do that. All right. This is our subsystem. Probably not going to touch this anymore. And this is very, very close to what our robot subsystem looks like. The only things I'm going to come in here and touch up are these tuning values. And like I said, we're not going to do a lot with them. I told you guys no tuning. You're going to do minimal tuning. So now the next part is setting up the look of your simulator. So right now you can run this and there will be no visual aid to tell you what's happening. It can run, but you're not going to be able to see it. So we just need to add this to Smart Dashboard. So I'm going to make a simulation package. I'm going to add a new file, mechanism simulator.java. This one is, if you've made any UIs in Java before, it's where it's just you're attaching a bunch of objects together and panels and roots and all that stuff. That's all this is. It's just knowing which objects to do. So you start off with this mechanism 2D panel, which is kind of like the window. Then you have to define the root of your mechanism, where your mechanism starts. Sorry, this will be a root. And once this is done, once we finish this class, root 2D, we will run it and we will see the arm do something. So we're almost there, guys. This one. Okay. Private final mechanism ligament. This is, they define them kind of like your actual skeletons. They call these ligaments. This is just the physical like arm. And then we just need an instance of the arm subsystem so that we can do this. Public mechanism, we're going to define the constructor. It's just going to need to take an arm subsystem. This.arm subsystem equals arm s. And we are going to build up our UI now. So this.panel equals new mechanism 2D. There are no units here. Like a lot of WPILib doesn't have units defined. That doesn't mean there aren't units. It means it doesn't care. And so when I said earlier that units are something you need to be keeping track of, this is one of those places. So you could pass in 100, 100. What does that mean? Is it 100 pixels? Is it 100 inches? I have no clue. Honestly, I don't think it's pixels because it isn't. So what I do is keep this in the same units as I do my mechanisms. So on the team, we typically do degrees and meters because we don't like to keep between the same systems of measurement. We should be doing like inches and degrees or something, but it doesn't really matter. So I'm going to say inches to meters, 100. And again, like I said, there are technically no units here. We are defining the unit namespace by doing it this way. Otherwise, it just becomes confusing, and I'll show you why. So then we define the root. We're going to call it arm. And again, this is the length of the arm. Oh, sorry, this is the starting position, the X and Y coordinates. And again, we're going to define them in, technically we're defining them in inches, but because everything is in meters in ours, I have to use the inches to meters. I think, so these numbers are pulled from our code. I'm pretty sure this is actually physically where the arm starts on the robot. It's like 7 inches up and 10 inches from the center. And then this dot arm equals root dot append. And you have to give it a ligament, an arm. We're going to call it arm again. How long is this arm? Well, we technically defined it in that sim, so an efficiency that you could do here is by making some constants. I didn't use any constants today. But it's 25 inches long, and I want the starting angle to be 0. I want the line width, so that this is just like making it look pretty. It's 6 pixels, I think. I don't know if it's pixels, again. And I'm gonna make the line yellow. And I'm gonna figure out why it's mad. Why are you mad? String double, int, color. Do I? Oh. Good call. And I need to import this. Thank you. Now we're happy. Okay. So this constructs the panel. We just need to update it every cycle. And so I do that by saying periodic. I'm making my own periodic method here that we'll call. We grab the arm state from the subsystem. We import arm state. So again, now we know where the arm is today, and we're going to render it to the screen. So all I do here is a quick null check. Again, I could have kind of defined this as optional, but this is a safety thing. We take the arm ligament that we did, and we set the angle, and we just say current state dot current angle. And almost done. I need to now just add this to Smart Dashboard. I'm going to use Advantage Kit to do that. Like I said, the only difference I made from a bare project is I added Advantage Kit to this to make this a little bit easier. Chord output, robot simulation, and panel. Quick other deal. I need to just real fast private final mechanism simulator sim private final arm subsystem arm semicolon. Here's the cool bit. If robot.is real Oh, I did actually. I added a parameter here, so I could do this way. Is sim, you can see it right here. Arm equals new arm subsystem. And then we have to pass in an arm IO. Import. Thank you. And we need to say sim equals new mechanism simulator arm. So you could use this simulator with your real robot. We use this actually to kind of visualize what the robot is doing in real time as well on our dashboard by using the real values when the robot's driving, but you can also do that here. Else arm equals null. This is just a little bit of a shorthand there to make that fixed. And then finally, we're just going to make this public to save me a little bit of time. In the robot, we've got this robot container already defined. In here, right now I'm just saying is true. You would probably put robot.isReal here. And then all the way in the method that already is defined, the simulation periodic, I'm going to say robot container, is it robot container? Probably. Dot sim dot periodic. And I'm just double checking that that's all I need to do. Now, first let's see if it builds. Fingers crossed. Fingers crossed. The fun part here is that the elevator is almost exactly the same code. And I'll show that. So you hit simulate. There's an option here for simulate robot code. It's going to pop up a little screen that says, do you want to use the driver station or do you want to use the sim GUI? We're going to say the sim GUI. And this is going to be exciting and not exciting all at the same time because we need to do one more thing. There's my arm. It's not doing anything right now because we never commanded it to. In fact, you see I turn it on and gravity happens and it falls. So if I real fast, I'm going to use some values that I already figured out for this. So 0.001. And this is the tuning that, like I said, you aren't really doing except to get something working here. What'd you say?
Proof of concept.
Proof of concept, exactly. We're gonna refresh that. Now when I enable, it should go to 45 degrees. You see it moving there? Awesome. That was fun. That's simulated. We're gonna do one more cool thing that I can show you guys. This is now you've got this done, you can start building commands and doing the scaffolding for your robot without a robot. And you do that by going into your robot container and you just say smart dashboard put data arm 0 and we say we got to cast it, unfortunately. Sendable this dot arm dot set arm position 0. And I can't do that. I add that. I'm trying to make more of these. 45, 90, 135, 180. Let's do one more. Oh, there is one right there. 180, and we'll make this one 225. And we'll ignore the fact that I did those, put that 225 in the middle of it all. Save, rerun this. All of these end up in this menu up here, network tables, smart dashboard, and they're all here. Now I made these when I made this project before, so they might still work, we'll see. So I enable and teleoperated, it goes to its default state, which is 45. This button right here says 0, goes to 0, go back to 45, go to 90, go to 135, go to 0, go to 180, go to 0, go to 225, go to 0, and you've got all of that. Now, you put this all together in that mechanism simulator class, where you can actually, using those ligaments, add the elevator, for example, to this, and it'll move up and down. It is almost 1 o'clock here. So if you need to go, you can. I'm just going to real fast find the other project. Because I went too slow. Or I made this too long, one or the other, probably that one. But that's okay. Because like I said, I will commit this. Actually, here's what we'll do. Let's see, is this gonna run?
Just while he's loading. The other cool thing about using this I/O object that he's showing you guys, if you just simply make another instance of that I/O using the physical hardware, all the infrastructure is already in place now, that when you run the real robot, you will also see it, like he was saying, show in the simulation, all at the same time. It's all just replacing a simple object to make it represent the real thing. So we use this a lot in 930 to help us kind of get to a good place. Or if the robot for some reason does something bad, and in our simulation, it does something different, that can also help you find problems in your code.
Let me show you one place where we definitely did this and it helped, like in a pinch. So we had this code in here. This enables continuous input. What this does is it means that the controller knows that 0 and 360 degrees are the same position. And so it will know that, like, maybe if you want to go down, instead of doing whoa and then going there, it'll go down. It'll find the shortest path. Our robot, when we go to intake from the chute, we flip it backwards and kind of go down at 270 degrees. We actually, if I enable teleop, so our intaking kind of looks like that, where it puts the arm backwards. We had this set enabled continuous input, and it finds the shortest path, and watch what happens when I hit 0. It travels through the bottom of the robot. So it tried to do this on the actual robot because we didn't check this. And it collided through itself and was very upsetty. And we're like, why did that happen? Who knows? And we booted this up, played with the buttons, and we watched. And if I do it like here, you'll notice it also goes back. It finds the shortest one and drives straight through the robot. And that's what it did on the real thing. And it didn't like that, obviously. So that is there. I might just switch computers if this runs. But it is 1:02. I think this is the last presentation of the day. I appreciate you guys for trying to comprehend what I'm saying. I know I moved a little fast, but the simulator here, like I said, is really meant for stringing together all of your logic before you get the actual robot. In 2022, we didn't use this exact method here, but we used the simulator to scaffold out our entire end game sequence. So if you remember 2022 is the monkey bars, and we built a windmill climber, which means we had claws on either end and the thing just spun to go between. And it used sensors and all this stuff to do it automatically, so the driver only had to hit one button. It drove until it saw a sensor, closed, rotated till it saw the sensor, closed, let go. We did all of that in simulator so that the first time we actually put it on the robot, it did the entire sequence first try, which was better than it did at week 6. But that's a mechanical problem. And in this presentation, I'm on the programming team.